And we are live. Hello, everybody. Good morning, good afternoon, depending where you are. So, I'm doing a very quick intro today because I have to be honest, I don't know anything the back end of simulation. so, so I will probably also be a listener with some other people on this one and excited to see what you have to share with us today.
Yes. Hi, everyone. And you can see Dani is morning because it's very bright. For me, it's already afternoon and evening. Yes, about the simulation, back end, even front end, not everyone understands. And what is also very surprising, usually people that actually need to use it somehow get super overwhelmed with this. So I decided that to give a very short intro. I've been working as a simulation engineer. I've been working with a simulation for the past 13 years. When I did the research first in Dresden, and I did my PhD there, so we worked with the simulation X, so I worked with some CFD simulations and so on and so on. And I see that a lot of people don't know what it is for and when to use it. Or sometimes maybe not to use it at all and just stick to old paper calculations that actually also don't true. And today I also spoke with a colleague of mine, and he reminded me. He said, like, remember that pneumatics is always, and compressed air is more complex than hydraulics. So even if you want to explain something hydraulics, and that's true, a lot of calculations that are coming from hydraulics, and it's not correct. So, and this is what I'm also trying to bring awareness from the academical perspective of view. It's two different fields. Don't treat it as the same, and we will have also a separate conversation about it. But I want to share with you in general what type of the simulations again I worked with, and this will be everything about the flow. It will be about the air itself. So I'm not going to talk about the construction. I will not talk about the simulation of the ceiling and so on and so on and so on. I want to talk about the flow simulation, meaning when we have main parameters such as pressure, flow, and temperature, those three parameters that we can calculate, and the energy and so on and so on and so on. I want to show you for what it can be used. And for that, let me share my screen, and then we'll see, so people don't get so overwhelmed by simulation. Okay.
Here we
Good.
go.
Do you see now my screen?
Yes.
Okay, great. So this is just to give you some reference of the project from the university where I used to work before. But I just wanted to show you what exists. So we all know about we've heard something about the 3D simulation. And I see very often suppliers of components, they're like, oh, we need 3D simulation
Yes.
right now to understand something. What is actually 3D simulation? You also can find it, it calls also CFD. So here you can see it is the computational fluid dynamics. And this is basically, it's a whole field. Even I worked as the simulation engineer. I actually didn't work in CFD. I only know what it is. And whenever I need any CFD simulation, I go to my colleagues. So before it was my colleagues at university where I work now. And basically what it is about, the CFD simulation is the 3D simulation. And usually it's used for the optimization of the geometry of components. Since we have only 20 minutes for the coffee, and it's not a lecture on the simulation, but this, I just want to give you the flavor of that. Basically, it's here you see the flow. So it's like the photo of the flow, and this was the optimization of the vacuum ejectors. And here you see the simulation. So basically, it's a 3D simulation of the flow. If I super simplify it, so please, any academics that are watching it, switch it off right now. We take a little cube of the area here in the flow, and then we have the 3D simulation, meaning that we can see the full 3D flow, and we can see the pressure, temperature, and as well as the flow distribution within the component inside of this. So meaning, for example, you have a nozzle. So this is the ejector, for example. Even if you have a nozzle, you can see the entire distribution of the pressure, flow, and temperature inside, let's say 3D, inside this component. For what it is important, first of all, it is an essential tool for the component suppliers. So component suppliers, engineering, R&D departments, you need to use it because in pneumatics, unfortunately, in compressed air and pneumatics, because there is such a big theory gap, and this is true. So this is also a lot of suppliers are telling us everything happens experimentally, meaning that you're spending a lot of money on the measurement, and a lot of data that you also find in the catalogs, it's actually measured data. And it's good, of course, when there's measured data in the catalogs, but the moment you change tiny pressure, flow, and other systems, things, the performance of the components also changes. And this is extremely important, like just to save some money and not testing every single thing. And not communities have also this opportunity to test the end users. It's extremely important for the development of new component. What you can achieve through the CFD, if we take one single component, you can, for example, optimize the heat transfer, so the components doesn't heat up so quick. You can also you can increase the flow that passes through the components, or you can reduce the flow that passes through components. You can improve the vacuum performance of this, or you can improve, for example, the blowing force performance. So this is everything what the geometry has an impact on. I recently spoke also with a colleague from our field, and he's doing some project for the nozzle calculations, and he told me it's impossible to calculate. It has so many parameters. It does has many parameters, but the moment you get the correct model, it actually calculates it for you. So, and this is extremely important and shows the level of the suppliers and the level of the engineering. So, once CFD helped us to optimize the component, then we can go into the 2D simulation. So we're downsizing our simulation, and now we have here the component as a black box, meaning here I can optimize how much flow passes through this, what is the inlet outlet pressure, what is the pressure drop, because here I also can model the friction of the material, meaning I can simulate the material of my component also. And again, this is extremely important for the suppliers of components, for the companies that are using new products and so on. You can also check when the component after 20 years, 10 years, what is the mean time of failure, for example, of the component. So all this extremely important information and data. Of course, every simulation has to be validated by test. But let's see. Now we optimize the components and we know what is the pressure drop, meaning P1 enters here, P2 goes out here, right? I have my components inside the system. Here I have supply pressure, and I have here, for example, the output, in this case, it is atmospheric pressure. I know the flow, and I know the pressure drops. I also know heat transfer and so on. So meaning that now in 2D simulation, I consider my component more or less like as a black box. I have an input, I have an output, but I can know the different flows and curves over the time, for example. Or I can see the dependent on the pressure and the flow. And in general, it's extremely important to know the things like, let me show here, let me go back. So meaning that I put now these components as a part of the system. And now I consider the component as the black box with input and output. And I have, as it calls, the concentrated parameters simulation or lumped parameters simulation. So meaning that I have input, output, and I have parameters of this component. What it gives us? It gives us the curves of the flow pressure distribution over the time. For example, here the tool, the online tool that we developed at university, and here is the tool for the simulation of cylinder behavior. Also have tool for nozzles, for various different components. So we have already the geometry of cylinder, and we know if I put the pressure 6 bar, for example, 95, 98 psi, how it will behave, what will be the pressure drop in the cylinder, how the pressure will behave, what will be the output force, what is the consumption, what is the flow, and I know the distribution of the pressure during the cycle. For what this kind of simulation are important? Extremely important for new processes establishment, for example, for new production lines. In general, wherever you design in any new processes, it's extremely important to know the dynamic behavior, because I want to know how the cylinder behaves at the end of the stroke. What is the cushioning performance of this? So I can optimize the soft stop of cylinder, right? At the end stop, I can make the cylinder move smoothly at the end of the stroke. I also can check the pressure oscillations. For example, I have a very precise operation where the cylinder has to stop at certain moment. I know the dynamics, the cycle time, and it's also extremely important for the suppliers of components and systems, as well as for the users, the producers of the production lines. So this is extremely important. So meaning that I still have my component as a black box that is already designed, but I consider it. I already know the friction parameters there, the loss parameters, and so on and so on and so on in this component. But putting it inside the system, I actually can see the distribution over the time of these parameters. Extremely important for any dynamic systems, new systems, whatever any production lines are developed for producers of pneumatic systems. Please pay attention to this. This is extremely important and very, very useful too. And then we have a 1D simulation. The 1D simulations now my component is a really black box. So meaning that I have only input and output, and instead of calculating seeing the curve of pressure distribution over the time within a cycle, I see the maximum pressure. I see the minimum pressure. I see the maximum flow of this component. And I see for example, the consumption of this component. Absolute maximum of minimum or medium value, depending on what is the goal of the simulation. And this is extremely important when we actually have entire pneumatic system and many components put together. For what it is used? For designing correct pneumatic systems, choosing correct cylinder, correctly choosing valve for cylinder, the piping, knowing consumption of this, knowing the pressure set point, know the blowing force of the component. So here I have only one parameter for each component. I have one parameter, and this is absolute parameter: the flow, the pressure, and any I would say task parameters such as force or any other blowing forces and so on and so on. So this, what it can give you, it can give you for what it is used: for the optimization, for the correct sizing, for checking the systems. You cannot improve the performance of the component, but you can improve performance of the system here. So meaning that, for example, I have here pressure. I can check also the entire system, and I can see, if here I improve and I change the components and I replace components with a better performance, I can save for entire system 140,000 euros. So this is used for the end user. So it can be used for the production line manufacturer to give also the parameters for the finally the end user, because very often we see, not very often, but I would say always, what usually the production line supplier gives to the end user, to the factory, is the required pressure level, and that's it. No flow, no information. We see also very often that production lines that are new generation, they consume more of compressed air than the old lines. And this is simply because the mechanical operations in this line were replaced by pneumatic components because it's cheaper, and production line supplier doesn't pay money for that. That is also logical for the consumption of compressed air. And this is why they don't give information about this consumption. But there is a huge opportunity to reduce this consumption by simply simulating, performing the 1D simulation. You can tell me that for audits, you can do the calculations of back on the paper, Sure. I would like to see this back of the paper because how it has to be done is we have the parameters of each consumer or component, and then we need to calculate every single component that is backwards until the pressure flow or any compressor. So this is extremely long calculations. Plus, it's not a simple calculations. It's all compressible fluids. So the 1D simulation actually can improve both systems and the systems of the single axis system, as we call it, cylinders, motors, ejectors, and so on, and the entire production lines and entire compressed air system. So this is why this is maybe used mostly for the end users, for the factories, producers of production lines. And this is basically why it is also important. I see very often that a lot of companies claim use of AI. I think it's very good. We also use AI in our company, but the AI has to be used only when the boundaries of physics are reached. Meaning that if we know the physics and how the component behaves, and there is description of that equations, and you can actually model it using 1D, 2D, 3D simulation, you don't need the AI. You need to have when you need to classify a lot of data, collect the data, analyze this data. But it has to be all based on the models that are validated and not just from wherever. I don't know. I see a lot of the compressor suppliers, producers of some cylinders, that then we're using like AI to do that and that and that, but there is no even data that was trained on that, or just a few. You cannot train data just on 100 audits, for example. So it is not enough. And this is why it is extremely important to understand why the simulation is needed. And I want to say that it saves a lot of time and it saves a lot of money. The extremely essential part, because nowadays it's still all measured, but it's not all measured also in a aligned way. So this is why I think it's extremely important to pay attention to this and not get overwhelmed with this. There are many tools. For example, if we talk about the 2D simulation for the entire systems, there are tools like Simulation X. There is ANSYS automation studio that mostly on the signals, not the physical calculations, but like pneumatics has a lot of logical, so you also can have a lot of logical circuits. You can check also some logic there, programming the SPS systems for that. The 1D simulation is it's essential because in this way you can optimize your system from the consumption to performance, checking the forces, checking all the essential components. And the 3D simulation is extremely important for the suppliers of components. Whenever you want to adjust, change, modify your nozzles internally, you need to first perform this simulation, validate it, and then you can have the simulation run. And imagine that for that you actually need to manufacture a new nozzle with a new geometry. Without simulation, it's just a waste of money and of time. So this is a very short intro, and we'll be doing more like scientific, I think, coffees or separate workshops on that, so I can show the real cases. But I just wanted to show today for which application and when, for which needs, what type of the questions you have. Please don't put AI everywhere. It will just ruin your system. So most of the time, it's a good tool, but you need to train it on so much data. And since there is not so much data on our systems, and I'm sure that single manufacturers also don't have it. It's 100 set points, 1,000. It's not enough for that. So
Wow.
this has to be way, way more. From everything from my side for today.
Yeah, I don't even know where to start with that. I mean, it was a very good intro, like basics that I could mostly understand. So that was good. I'm curious if anybody watching or watching this later has any questions on it? Because I know this was just scratching the surface. Um,
But it's scratching the surface for sure. I mean, people are specialized. I told you I worked with simulation for 12 years, but I never do the 3D simulation. It's not my specialization.
yeah.
So as I have colleagues that do CFD simulation, but they don't do the 2D simulation. So it's completely different fields. So, but it's if anyone has some task that you're working with, just ask. Maybe you don't even need a simulation. Maybe just a simple calculation is enough. We have a very good interview now with Martin Pitcher from Emerson on our YouTube channel, where he talks about the design methodology, and it's really really good. So it's really nice method where you actually can start designing the systems without using any tools, just a piece of paper and a few experts that can sit together and discuss it. So it's very interesting because you can understand all the risks, but then when you want to save time and when you want to save money, instead of measure all the time or just putting some nonsense in the catalogs, you can just use this simulation. So have an expert on that. And this is, I think, should be really introduced into our field in compressed air and pneumatics, because unfortunately nowadays it's not the case in the practice. And look at the companies that are thriving. Look at the companies that have more revenues. I'm not gonna call the names, but they have the companies that are on the top. They have top experts in the simulation of compressed air. So simulation and the engineers that know thermodynamics but not hydraulics. So just make this parallel and look for some companies with the blue logos. They have their especially pneumatic cylinder manufacturer. They have more and more systems. They have really great experts. I had an opportunity to work with, and they have their own in-house tools. They use other tools, but they understand physics, and this is why it allows them to improve better and better and manufacture better components, because they save a lot of time on the trials and errors.
Amazing. Okay, I think that's a good stopping point for today. We actually were closest, I think, today to the 20 minutes.
Yes, I didn't want to make it like 30, but
Yeah,
it's good.
no, it's perfect. All right. Thank you, everybody. You know where to find us. If you have questions, DM either myself or Dr. Elvira. If we have had some people reach out to us that they would be interested in sharing some of their expertise here also. I have had people recommend other people also that will be on. So please reach out to us. We're fairly open as far as the different topics. As long as compressed air is somewhere in there, then we'll talk about it for sure. But you know where to find us. And until next time, we'll see you later.
Thank you. Bye.